Hello community! Let's do some crazy new AI because I feel today I want to build something new. Now you know we have a problem because global corporation, poor Meta, poor little Google, poor little Microsoft, they are running out of training data for the next generation AI system. And you might say, hey, why? We have 8 billion humans that generate here more nonsense every day. But unfortunately, they are now mixed with AI-generated content, and we just have a repeat of the same old stories. So, yeah, imagine even some original raw data that would be nice and brand new. They might be legally protected, so we are facing a problem. But not for long, because we have hundreds of millions of video data with trillions of visual elements in those videos. Now, you know we have object identification and pixel segmentation AI models, where we can combine those AI systems as agent now with our most advanced semantic language model. So this means we can alter each and every video content in any way that we want. This means we can generate synthetic data. And those synthetic data are then, for the next generation AI, the new training data. And we don't have to go to Facebook or WhatsApp or any other platform where they just have the same old stories. So, new paradigm. If we can think of a scenario, absolutely brand new, unseen data, go crazy with your imagination, we can build it as a synthetic data. And the more synthetic data we generate, those data we can accumulate to a training data set for, let's say, a video sequence. Now, there's a little tiny insignificant problem if we say we, because we means that I need some tools, and this is my tool set. A large language model, a vision language model, a diffusion model, a policy network for the reinforcement learning. Maybe I need a super resolution model to increase the resolution here of my video frames, an object detection model in our video sequence, and of course a segmentation model that we see if we have a video sequence, if the car moves now, that we can segment it out in the time frames. But you know, this is all what we need. And now let's build something. We have so much theory. Today we build something. And what is the easiest thing you can think of? Let's make it so simple that everybody can follow. Gemini Pro, vision language. We go with the old-fashioned clip vision transformer. Diffusion model. Look, we go with a 1.5. My goodness, this is from the Stone Age. For a policy network, we take our workhorse, a ResNet 18. Where I have to say, if you are starting your green grasshopper here, you will not know what a ResNet is because this was 2014, 10 years ago. So, refers to a specific architecture we used here in the good old times, and reinforcement learning combines here convolutional neural network with a multi-layer perceptron to form a policy network, which is used to determine the action of agents, that actions they take in a given environment sequence. Super resolution is just an upscaler 4 times. Object detection model, we take the very old OWL, and for the segmentation model, we go with the very old FastSam version 1 and clip segmentation. Now, if you are not familiar with this, never mind. Look, here, for the panoptic image segmentation with vision transformer, I have here the complete code. You can do this, you can identify here each and every person, you see? Each and every object, like handbags, so easy, we have the code ready. Stable diffusion, clip, no problem, here's the video for you. Clip, unit, variational autoencoder, vector quantized variational autoencoder, here's the complete code. Build stable diffusion and whatever. Vision transformer, here. Fine-tuning for object identification, our PyTorch vision transformer, free Colab notebook, great! The latest in diffusion models, well, it's some months ago that I did this. Stable Diffusion 3 was at this time the latest one. I explain here how do they work, diffusion, transformer, and if you want to go to the very latest research edge, I have symmetry breaking in AI diffusion with discovery if you work here with the mathematical theory of spin classes, theoretical physics for diffusion models. And from Stanford University, we have the control net explained here. So there's everything available for you. This is just the old tools that we have in our toolset. Now, if you're not familiar with fast segment anything, never mind. This is here from June 2023. This is here on SAM. And you might say, hey, we have now in August 2024, so why don't we use SAM2? And I say, okay, let's use SAM2. But listen, if we use SAM2, then, you know, what we also have to do, we go with the OWL, the version 2. So scaling open vocabulary object detection by Google DeepMind, May 2024. OWL version 2 is, just like its predecessor, a zero-shot text-conditioned object detection model. And OWL VIT uses CLIP as its multimodal backbone with a VIT-like transformer to get the visual feature and a causal language model to get the textual feature. Old stuff, you know this. Code is so simple that it's even here on Hugging Face. This is all the code that we need to do this. If you want to see this, 2 days ago here on Hugging Face Spaces, Murph did here a fusion of both models. It's real nice because, you know, the new SAM2 does not accept text input. But if you combine it, if you merge it here with OWL, the version 2, look, I have uploaded here an image and I have here, I say, identify the computer screen in the image. And you know, this is a synthetic image. And you see it's not perfect. It is absolutely missing parts. But yeah, okay. Oh, gee, my goodness, we have, I don't know, 50 computer screens? What happened? Oh, confidence threshold. I set the confidence threshold to 3%. Okay, let's improve this 50%. And we have here the 2 computer screen, even from a not realistic image, from a synthetic image. But you know what? The transparent monitor was not detected, was not identified. So now we have to train the system, and you might say, hey, do we have to train SAM version 2, or do we have to train OWL version 2, or do we have to train them together? Well, this sounds interesting. But for my green grasshoppers, at first, object detection. What is this? If you're not familiar with it, it involves identifying locating object within an image, within a video sequence. The model outputs bounding boxes around the detected objects and classifies each object within the box. And we have image segmentation, like I've showed you in my video already. Involves partitioning an image into segment or region that correspond to different object or parts of an object. And this provides now a pixel level classification where each pixel is assigned with a class label. And here we have, in the simplest case, a semantic segmentation. So each pixel is classified into a class. Let's identify all the cars in an image. Or you go with an instance segmentation. So we have object detection and semantic segmentation by identifying individual instances. That's all there is to it. So we could go now and say, hey, for the object detection segmentation, we could go with some much more advanced, you know. But no, I'm doing this. No, we go here with the classical published version here, end of July 2024. Google DeepMind and Imperial College London published this new Diffusion Augmented Agents. That sounds interesting. So you say, what kind of diffusion model, an image generator? If we do this, how can we augment the performance of our AI agents in reinforcement learning? Well, it turns out with the new methodology by Google DeepMind, what they call Diffusion Augmented Agents, they train now the reinforcement learning agent in a very particular way that we do not need. We have no problem with training data. We just generate everything synthetic from video data. So this is the framework we're going to look at. We want to improve here the reinforcement learning performance of our agents in a multi-agent framework, whatever they do. So what do we have to do this? Autonomously, you know, reinforcement learning, we need rewards to compute now those rewards for both seen, that's easy, and unseen tasks, that's really difficult, by fine-tuning a vision language model, okay, on data augmented with synthetic samples. Okay, so I say, okay, I take my vision language model, and if I have new syntactic data, I just can fine-tune this. This is simple. But you know what's really interesting? Those syntactic data, they are here generated by a diffusion model. But the diffusion model itself is coordinated by a large language model, and the large language model is analyzing the task that we will give to the model, break down the task in simpler tasks, and check here with a vision language model and a diffusion generator how they can build new syntactic data. So what we do, if we explore or learn new tasks, and this is beautiful in robotics, the robot enters a new room, a new environment, and we have a given task and maybe some goals or sub-goals. So how can now the robot learn without human guidance? How is it possible that there is an autonomous learning? And there's a beautiful idea that you say, well, we have recorded observation. The robot has already been in 10 different rooms and experienced there and learned there every different kind of object, how to handle those objects in the room. And now we are in room number 11. And now if we look around, maybe we find something that's a little bit similar. And then we can modify the video sequence and generate new video data for our vision language model to learn. So we do this via diffusion models. So what we achieved now, we have transferred previously collected data from our buffer from the last 10 rooms to a new task. And this sounds interesting without human supervision. So, from the original paper, simple idea. You have a task. Put an apple on a red chair. Okay, so we have here our system, and the LLM comes in and says, hey, yes, of course. So what I have to do? First thing first, I have to find an apple. I have to pick up the apple and find the red chair and put the apple on the red chair. So let's see. In my offline data, in my video library, in my, SQL, whatever we have, I'm looking now if I have some episode of experience, past experience. And then I use here a vision language model as an LLM, and I give the VLM a task. I say, hey, do we have those training data available in our memory somewhere, in our buffer? And does it match what we need? So the VLM is now doing an embedding. It is taking here the first sub-job, transforming it here in a vector space embedding, and looking on all the visual data that it has. Do I have a corresponding image or a short video sequence for this? If yes, I say, hey, I have for the first job, for the first task, I do have a video sequence we can use, goes in a new buffer. If the VLM says, hey, I calculated the cosine similarity here between here the textual embedding and here the visual embedding, and I have to tell you I'm below the threshold, LLM says, never mind, okay. So I say, as an LLM, okay, so I have to generate syntactic data for my second part job. And then I say, hey, diffusion model, listen, I need you to generate here a short video sequence or an image with this and this content. And then our diffusion model will generate exactly the video sequence we need for now the second job. And I put this also in a new buffer. So you see, for my complete job and all the sub-jobs, I have now in my buffer here a linear sequence, and I hope I'm able to do and solve the task given. If you like to see this here in a circle, beautiful. Here for my green grasshoppers, again, another explanation. But let me give you here a feeling for what we are doing. Here, top, we have the original. So the job is here for the robot arm, and you have here a camera here, as you see this. Pick up the, whatever this is, little coffee cup in green, and put it here so that I can, on this tableau, so I can refill coffee. So you see, identifies it, picks it up, and tries to put it here on this shelf. Now, I will show you that a year ago, we had a system called Rosie. And Rosie took this, said, okay, so I have now to substitute this green coffee cup here with, let's say, a red one. So it generated here in the video sequence, you see, this is a dark red, this is here a lighter red, this is here a non-white interior of my coffee cup, this has a white interior, there is now some lighters printed on my coffee cup, but you see the perspective is not right. But now with the new system here that Google developed just 4 days ago and published this, you see the cup stays the same. The cup is now always the same red cup. Maybe the little white here, yeah, circumference here. But otherwise it has the same shape, it doesn't change. So we have a geometrical consistency and a temporal consistency for our time series in the video sequence. And I thought we were much more advanced technological. Because look, if we have a video sequence here in the buffer of this system where the original is stack the blue cube on the red cube. So you have here a red cube and you have a green cube and a blue cube, and then we have the robotic arm, and the robotic arm is now taking here the blue cube and it's putting it right on top of the red cube. Beautiful. Now you tell the system, hey little robot, listen up. I want you that you now stack the blue cube on the green cube. The robot is gonna tell you, hey buddy, I would love to do this, but I have no idea what you mean. You have not provided me with visual training data, video sequence or images that I can see how this looks like. And I cannot interfere, hey, this looks like a cube and a cube comes in 25 different colors and the colors go from red, blue, green, whatever. And I can identify this. No, I need training data is what my little robotic system tells me. So we have now to generate, for the second case, stack the blue cube on the green cube. We have now to build this video sequence or this image. So the robot understands then, okay, this is my target image. And now I have to do this in the real world so that I have exactly then this composition. And if you think that you can say to a robotic arm, hey, grasp the green cup, that it was trained on this, and then you say, oh yeah, by the way, there is also a red cup, please grasp now the red cup, the robotic arm will come back to you and say, hey buddy, where are the training data for a red cup? I know what is a green cup, but I have no idea what is a red cup. So you see why we need this diffusion data, this additional training data here, and why now we have this combination of a large language model, of a vision language model, and of a diffusion generator, of a diffusion model to generate this missing training data. My goodness. There's a very beautiful site here. I recommend sitesgoogle.com, view Diffusion Augmented Agents. So you see we have a video sequence where a robotic arm takes an apple and puts in here into. And then the next task is an unseen task, an unlearned task is take an orange and put the orange here into this glass something. Now you have to generate visual training data that the robotic arm can do this. So here we are now with diffusion generated, augmented training data for our agent that if our robotic arm was just trained on an apple, now we generate the training data set for oranges. My goodness, I thought we would be much more advanced in robotics AI, but okay. Now, if you are a genius, you remember that in February 2023, we had from robotics at Google and Google Research, and we had Rosie. And Rosie was scaling robot learning with semantically imagined experience. And you remember, Rosie, semantically imagined experienced Rosie, was exactly doing this, but we had a human in the loop, and the human identified, said, hey, this is the cup, this is the cat in the image. So we had here a high human involvement. And now, more than a year later, Google publishes, if you want, Rosie 2, version 2, the update where we get rid of the human involvement And now we have an LLM coordinating a vision language model and a diffusion model. Remember Rosie? Look, we could morph all the background, all the object that we wanted in any way that we wanted. But we had visual geometry was disturbed and the temporal flow was disturbed. So this was Rosie. And now we are ready with our vision language model and our diffusion models to go the next step. So again, Rosie, beautiful. And now with the new DAAG, entirely autonomous, both in terms of detecting the accomplished task via the vision language model and proposing and generating augmentation, augmented data, augmented video streams via the LLM, querying now the diffusion model. The LLM tells our diffusion model, hey buddy, I need you to build a new video sequence for me with now a red cube instead of a blue cube or whatever. A car instead of an aeroplane, you can imagine. Plus, and this is the beauty here, they have now a diffusion pipeline that is both geometrically and temporally consistent when modifying here the video data. Real nice. Now, if you started here February 2018 with OpenAI, you might remember there was something called, and they already investigated reinforcement learning in 2018, and they developed a technique called Hindsight Experience Replay. And this was something real similar to this, and they had more or less the same problem. And by the way, if you go in exactly this paper from 2018, they explain to you reinforcement learning, and they have here the optimal policy for the Q learning, the Q function, the optimal Q function, and they denoted this the Q star in 2018. So if you want, about a year ago there was a hype about Q star. My goodness, this was simply here the publication from 2018, and then they jumped to deep Q networks here. Yeah, this was here the pseudocode if you want from 2018, but now we can go a step further. So the old Hindsight Experience Replay proposes here a method to reuse past recordings that solve tasks different from the desired task. And if asked to solve a specific task, T for task, the step N or the version N, but solving instead a task T, now the version M, during exploration, proposed to relabel the episode as if the desired task was now TM, therefore repurposing a trajectory from the old task as a success for a different task. Now, this was not so much successful as you can imagine, because you were looking to real similar tasks. But now we have something that we call Hindsight Experience Augmentation. So we go from Hindsight Experience, just a replay. Now we can generate and modify our video streams in 2024. Hindsight Experience Augmentation. So differently to 2018, when we're in the same situation, our method now modifies the collected observation that solved the task TM to synthetically generate an episode that would have solved the desired task. This simply means we can generate data, synthetic data for a specific task without the need to solve anything at all. So beautiful, we have now objects we have never seen before. We can generate those synthetically, retrain, fine-tune here our vision language model and have a perfect detection rate. Now, let me give you this idea how to proceed. I want to give you the list of the operation in a logical order, in a process order, and I would like to explain here this DAAG framework here, step by step. On the right-hand side, you see here all our tasks that we're going to explore. Task instruction, decomposition, experience collection, the buffer management of our recordings, of our old historical recordings. Here are our 10 different rooms that the robot already has learned and experienced something. Then we have this new Hindsight Experience Augmentation where we build new generate data. Then we fine-tune with this new training data set where we have now the blue cube put on the top of the green cube. We can now fine-tune the vision language model. For our reward optimization, we have a policy training and an exploration, and then we have autonomous guidance. So let's run through this for my green grasshoppers that you get a feeling what is happening in this framework. Task number 1, instruction and decomposition. I give here my little AI agent, Triumvirat here, a natural language task instruction. I say, hey, go to the fridge and bring me, I don't know, some yogurt. So the LLM comes now and interprets the task instruction and decomposes it into a series of manageable sub-goals. So, I don't know, let's say, okay, go into room number 14, find in the kitchen the refrigerator, learn how to open the refrigerator, look into the refrigerator, find this particular product that is called a yogurt, understand how you can grab it and put it on the table in front of me. Those are my sub-goals, and this is what the LLM is doing. Now, experience collection and buffer management. As an input, the visual observation and action from the agent's interaction with the environment. So we have now 2 buffers. We have a current buffer, a current learning buffer, where our steps are. And then we have, if you want, a lifelong buffer, stores all experiences in the last 10 rooms. This is just my example, but you have a feeling for this. And then this is here our lifelong buffer where we go and we say, hey, do we have anything that looks similar to a kitchen? Because maybe our robot has already been in a kitchen. So we can now say, hey, we do have an experience from a kitchen. So this is real close now. And we do not have to generate new synthetic data to simulate a kitchen environment. Point number 3, this beautiful new Hindsight Experience Augmentation. Input is whatever there is in our buffer, past experiences the robot experienced in the last 10 rooms, and the operation is the LLM reviews past experiences to identify observation that can be modified to fit the new sub-goal. Then we have the vision language model that calculates here the similarity, a cosine similarity between the sub-goal or the sub-task and whatever we have in our embedded visual encoder. And then if we have nothing that we can use, the diffusion model is then generating, building up, used to transform this observation, creating now augmented, modified, different color, different background, different form, different shape, different volume, whatever, that simulates here successful task completion. If we have this new data, we can now fine-tune here our vision language model. So the input, augmented data from the diffusion machine and the original observation, and then VLM is fine-tuned using this particular augmented data so that we now understand we are training now our VLM on a virtual kitchen environment, on a theoretical kitchen environment to improve its ability to recognize and score new task completion, new reward function. Remember, we're in here in reinforcement learning. And then you see 2 are left. So let's have a look. Policy training and exploration and autonomous guidance. Input here in policy training, rewards detected by now the fine-tuned vision language model and the collected experience. So the agent uses now these rewards and experiences to train its policy. Reinforcement learning. The agent explores the environment, applying its learned policy to perform tasks, and continuously doing so, collects new data and continuously learns. Autonomous guidance, sub-goals and task instruction from the LLM. The LLM autonomously guides the agent by setting and scoring sub-goals, ensuring the agent or the network of agents, the multi-agent conglomerate, operates without human supervision. That's it. So you see, we can build beautiful new virtual worlds to prepare our multi-agent AI system when it encounters a new planet, a new satellite life somewhere in our solar system, that the LLM, the AI system, is prepared. For my green grasshoppers, for the DAAG, if you want to see it here for a component, view or an interaction view of the component, I have this visualization for you. You see, I syntactically generate now a different training data set for you to understand, for you to learn. Gee, perfect. So we have our LLM, our VLM, and our diffusion model. And here you see all the tasks. The LLM is doing the decomposition of the task into the subtask with subgoals. It is responsible for querying here the vision language model and the diffusion model. And it is here in control. It guides here all the agent behavior autonomously. The vision language model has two tasks. It detects the rewards by evaluating here the visual observation against our task description from here. It fine-tunes using augmented data to improve here the performance, the accuracy of the AI. And the diffusion model generates here our new syntactic visual data that we do not have in our buffer by modifying a little bit, change the color, change the form, modifying past observation in our video sequence. And this they do in a very intelligent way, Google, by ensuring the geometrically and temporal consistency in the augmented video stream data. Great. Yeah, I know that this question is going to come by my green grasshoppers. Can you explain what is detecting rewards? Well, you know, we are reinforcement learning. So what is the definition? Detecting rewards, what I mean is involves recognizing that an agent has successfully completed a task or a sub-goal based on the visual inputs on the camera, on the sensor network, on the sensor array our AI conglomerate has, and the predefined task description either from me or the sub-goals from the LLM. And this recognition allows you, the agent, to receive a reward signal, positive or negative, which is crucial for reinforcement learning. Now, I'll give you here all the steps if you want to be a little bit more precise. So, detecting rewards, task instruction. The agent receives my task description in natural language, and I say, hey, little buddy, stack the red cube on the blue cube or the orange cube. My goodness, this will cause chaos. And now the vision language model input is that the agent performs actions in the environment and captures visual observation, images, video frames, whatever. And then we have simply clip. Clip takes this visual observation and my corresponding textual task as an input. And then the vision language model generates embeddings that you know. The embeddings here, vector embeddings, a vector space, 1024 dimension, I don't know, 100,000 dimension, whatever you need, what is suited for your particular task. So you have a vector representation for both, or a tensor representation to be more correct, for both the visual observation and the textual description. So we bring it together. And then we do what we always do. Remember vector spaces, RAG, cosine similarity. The VLM calculates the cosine similarity between the visual data, the visual embedding, and the text embedding. And if you have a high similarity score, this indicates here to our VLM that the visual observation closely matches here the text description. You can define now, when you code this at a certain threshold, 70%, 85%, whatever you like. So the VLM compares now the similarity score calculated here against the predefined threshold. And if the score exceeds now the threshold, very easy, the observation is deemed to match the task description, indicating that the task has been successfully completed. And if the VLM detects that the task has been completed, this means the similarity score is above our threshold, it assigns a reward signal, in the easiest case +1 or negative -1, and this reward signal is then used by the reinforcement learning algorithm to update the agent's policy, the old story that you know, reinforcing the action that led to the successful task completion. So, we need quite some compute power that this is happening within, I don't know, not within seconds, but some tens of milliseconds, okay? Let me give you an example. Pick up the red ball. Visual observation, an image where the agent robotic arm is holding a red ball. The process is, VLM processes the images of the front camera here on the top of the arm and the task description here in verbal generating the embeddings for both. We have a predefined vector space, of course. It calculates the similarity score between those embeddings, the visual and the text. If the score is above the threshold, recognize that the task pick up the ball has been achieved. The robotic arm is holding now the red ball, beautiful. And the agent receives a reward signal that is positive, saying, yeah, buddy, good job, thumbs up, reinforcing here this behavior. And we have achieved what we set out to do. Autonomous learning happened without a human intervention by using here the vision language model by the large language model with a little bit of help of the diffusion model to detect the rewards, and the framework reduces the need for manual reward labeling, enabling autonomous and scalable learning. And even if you want, you can learn things that are not even real. You can redefine reality. You can redefine historical events. You can redefine whatever you can imagine you can build, because AI will build it for you. And beautiful, I think this is it. This is the overview of our components and how they interact. Our Diffusion Augmented Agent framework leverages the capabilities of our vision language model, the diffusion models, and the large language model, plus the policy model, the ResNet model, plus you need here to have a better resolution of the images and the object segmentation and the object identification and whatever, but this is great. So now, if you want to know again, vision language model, diffusion model is a synthetic data generator, and it has a beautiful consistency. And our large language model is orchestrating the complete framework of all the multi-agent systems that we have, plus additional system, more about this in a later video, acting as the central controller, central intelligence that integrates here the capabilities of the vision language model and the diffusion model with the LLM. We have the decomposition of the task, the coordination of all activities, and an autonomous guidance for all the little agents that participate. And let me quote here the team of researchers of Google and something London. By repurposing experience from prior task, DAAG progressively learns each subsequent task more efficiently, requiring fewer episodes thanks to transfer learning. Finally, by diffusing unsuccessful episode into successful trajectories, change the color of the little box from green to blue. For related subgoals, DAAG substantially improves exploration efficiency. Through diffusion augmentation, experience gathered across a lifetime of learning can be repurposed, or think about all the YouTube videos that might be theoretically available to you, can be repurposed to make each new task easier than the last. AI. It will redefine the future, and it can redefine our past. I hope this video, you enjoyed it, you found some new ideas, you said, hey, that could be interesting to build for my particular application. It would be great to see you in my next video.